concept of continuity. All right, we've talked a little bit about continuity informally. If you remember, I gave you a definition of continuity that I could give a second grader and I think they would understand. Okay, and that definition was simply, if something is continuous, what does it mean?
Yeah, or you can draw.
You can draw without picking up your pencil. I could literally go into a second class today and say, hey, we graph things in high school. Pictures. And all it means is if our picture is continuous, you got to be able to do it without picking up your pencil. And then I could introduce like what it would mean not to be continuous, and I would show them like a hole. Not even show them a vertical asymptote, which I call a line that you can't step on or you'll break your mama's back, which I call a gap to a second grader. So it couldn't be a gap in the graph or a hole in the graph or a jump. Okay? And they would get that. But I'd have some little dink of a student in second grade that would say, Mr. Morse, your definition really doesn't work because I can draw a picture with a hole in it without picking up my pencil. And this is what they would do to me. They would go, and then my definition of continuity fails. So we need a more rigid, more rigorous definition of continuity. And I'm going to give you that today, which means the little canyons of the world would not be able to blow my definition up. Okay? So yes, it's true. You can graph it without picking up your pencil. And then I could blow them right back up. Because I'd say, okay, you little second grader, now draw your little picture without ever overlapping. And then they'd be stuck again. Because you wouldn't be able to draw the circle without overlapping back on top of it, so it wouldn't work anymore. No, you'd have to pick up your pencil. So, what is continuity? Well, I'm going to give you a very rigid definition for continuity, okay? So here we go. Suppose that F is defined in the neighborhood of A. Now, let me explain this idea of being in the neighborhood of something. That just means you're really what? If you live in somebody's neighborhood, you live what? Close to them, you know, you want to be in the neighborhood. It's like when you first start dating and you go out with a girl or guy or whatever, and you're at the movie theater and you want to sit by it. Like when you're in 6th grade, it was like, I'm going to get close to my girlfriend, and you like sat in this seat and she was like 4 seats over, and all our friends were in between you. And you like said, hey, tell her I think she looks cute tonight, and they pass it down the line and it came out like, he thinks you look ridiculous tonight, because you know how things get passed down the line.
Is that what you did?
Yeah, that was my life as a 6th grader.
Were you the one that changed it up? Challenge problems?
Yeah, I did. And so that's the way it went. You wanted to be close, you know? And when you get in high school, you realize the closer the better. So how close do we like? Get off girlfriend, boyfriends now. 0.001 close, okay? That's how close we like to be, okay? We want to be close. So that might mean to be in the neighborhood. Now let me read this again. Suppose the function is defined. Now that gives a little bit more to it. So now we're saying it's defined in west wind or weird wind. Okay? So if I live in the neighborhood of A, like over there in weird wind, okay? And I'm just saying, okay, in that part of the function has to have, all the points have to be defined in that neighborhood. That means when I'm saying at that point, when I say it's defined, I'm ruling out anything undefined, which means, that means in the neighborhood of A, by saying, yeah, no errors on your calculator, which is saying, basically saying, there's no holes and there's no asymptotes. So right away, I'm coming out and saying, hey, continuity. Suppose that the function is defined in the neighborhood of A. So we're saying continuity is tied to the fact that the function has to be defined. So anytime we see something undefined, we know that's going to contribute to not continuity, but discontinuity would be the antonym. Okay? I'm just getting all crazy today. All right? Suppose the function f is defined in the neighborhood of A. All right? So we're in the neighborhood of A, we're saying it's defined. So that's the first stipulation. It's got to be defined. Now we go and we say that f is continuous. So I hadn't even said it's continuous yet. I just told you it's defined. Some of you think if I just say it's defined, it's enough to be continuous. And I'm telling you it's not enough to be continuous. It's got to be more than just be defined. Okay? So now I'm saying we say that if f is going to be continuous at A, I should have put quotations around that. Let me do it right now. We say that f is continuous at A. Now we've already said it's defined in the neighborhood of A. So we've already ruled out holes in vertical asymptotes. Kind of. I won't even say for sure. But it seems like we've gotten rid of holes in vertical asymptotes, right? I'm going to blow that up in a second too, which is why this isn't enough. We say that f is continuous at a, provided that the limit as x approaches a of f of x exists. So, all right, we've already said it's defined, but now what is this saying? What is the limit as x approaches a of f of x existing saying? Huh?
The two sides agree when you're approaching.
Yes, exactly. When you say a limit exists, you say the left and right are what? You say the left and right are meeting. You're saying what it's approaching from the left and what it's approaching from the right have to be approaching the same value. So now you're saying, hey, it's defined and the limit exists. So now you're saying, hey, all the points are defined and now the left and right have to agree. But that's still not enough. This is why we go to the next part. And moreover, I love that word moreover. It's like, really? There's more? Okay. And moreover, that the value of this limit, whatever this equals, so if it exists, it has to equal a number, right? So whatever this equals has to be f of a. So now we're not just saying it's enough to be defined. We're not just saying it's enough for the limit to exist. We're saying whatever that value is that the function is defined at, and whatever that limit value is, those two have to equal each other. That's what continuity is, and you can't ruin this definition at all. This is complete now. This will complete your definition of continuity. So let's say, in other words, you know what this is saying, in other words? Let me just say it simply. F is continuous at A, provided direct substitution works right off the bat. So let's say, if you can direct substitute without doing any kind of funky algebra, without any squeeze theorem, without any further investigation, it works when you plug it in, you know it's continuous at that particular point. Now rises the question, how are we going to prove it's continuous at every point? You can't, because you don't have enough time. Because how are you going to prove it's continuous at every point when how many points are there? Most of the time, we're dealing with an infinite number of points. So how are you going to prove it's continuous for every point? You can't. So what you do is you do the converse. It's a much easier question to not show that something's continuous, but to show that it is discontinuous. We'll say discontinuous, not continuous. You can say not continuous, but discontinuous sounds way cuter. So it's a lot easier to deal with the question, not of continuity, but of discontinuity. Because I can look at a graph, and usually you're only going to have a couple of spots where it's discontinuous. You're not going to have an infinite number of discontinuities, because that'd be a stupid graph. Okay? You're going to have a few spots of discontinuity. You're usually going to have a finite number of discontinuities. So what usually you have to do as a student is say, all right, if they're asking me to describe continuity, if they're asking me to say where it's continuous, let's find where it's discontinuous first, and then just say it's continuous everywhere else. Let me say that again, because that's huge. That is like the key to the test Wednesday. For my continuity problems, it's if you want to figure out where something is continuous, find where it's discontinuous first, and say it's everything else. So if you came up with it's discontinuous at 2 and 0, you'd say it's discontinuous at 2 and 0 and continuous everywhere else. It's really that easy. Okay? Now, let me break this down into 3 parts for you, and I want to do these 2 things together, and then we're done, and then I'm going to go through the homework with you. To be continuous at a point A, let me tell you why these 3 things, why do you get into that moreover? Why you have to have all 3. You need to memorize this. Memorize it. Know it backwards, forwards, sideways, slantways, walkaways, every ways, okay? Even the new walkaways, even though that one was really weird. Okay, to be continuous at the point A, the function must satisfy these 3 conditions. Now let me go ahead and say this to you. On the AP exam, whenever you're asked about continuity, specifically if you're asked to show it, show means prove. You always have to show these 3 things. You are required to go through and make sure all 3 are true. because continuity doesn't work unless all three are true. Say it with me. All three have to be what? True. And if they are all tried and true, then you can show that it's continuous at that specific point. Okay? And they might just be saying, they might not even care about the rest of the points. You know how I said there was an infinite number of points? They might only be interested in one. They might say, hey, we don't even care where it is everywhere else. We just want to know what's happening at 0. Will you tell us what's happening at 0? And you'll be like, gladly. I'll go through the 3 requirements for continuity and tell you. Okay? And here's the deal. These questions almost always come up on the calculator portion of the test. And there's 17 calculator multiple choice questions. So you're like, sweet, I'm just going to use my calculator. Here's the kicker. On the calculator part of the multiple choice test, you only need the calculator for half the problems. And maybe not even half. All the other problems are theory problems that you really don't need a calculator for. So why do they put them on the calculator part? Because they're harder. They're harder than the non-calculator questions, and they give you more time on the calculator part. And here's the type of question they usually are. You'll love this. It's that 1 only, 2 only, 1 and 2, none of them. They'll give like a Roman numeral 1, 2, 3 and give you some facts about it. And you have write B checks. Okay? And they'll have like 3 facts about it, and it'll be all letters. There won't even be numbers in it. It'll be like f of a is c, and the limit as x approaches a from the left is c, and the limit as x approaches a from the right is d, and they'll say, can you show it's continuous? You know, and it'll be goofy stuff like that. So we got to get you used to this. And here's the key. If I can get you, first of all, I can get you to do it. You will have no problem with theory, because I am an expertise in theory. And if you will learn this, that's the first step. You got to memorize this. If you get this memorized, you understand this today, then we'll deal with the theory stuff later. We'll deal with the theory type of questions you're going to be asked. So here's what it says. To be continuous at a point A, the function must satisfy these 3 conditions. And we're going to talk about these 3 things down here before I even go through these 3. So let me go down, skip down just a second. Types of discontinuity. Let me tell you what types there are first, and you already know what they are. The first type is a point discontinuity. What is a point discontinuity, really? What do you think a point discontinuity is? It's a hole. Write that down right beside it. A point discontinuity is a hole. What is a jump? A jump? Okay, no. A jump would be where the left, a piecewise, where you'd actually have to, like think of your stairs, your step function, where you have to actually jump up from one point to get to the next. Okay, there's a little bit of a jump there. Okay, there's a break in that graph where you got to jump up a value. You're skipping over values to get to that next value. Okay, so there's no other name for that one. Infinite limits. Oh, jump sometimes can be referred to as a break, but infinite limits are really what? The reason to say infinite limits is because we know the definition of a vertical asymptote is if you have a vertical asymptote at, say, A, then you know as you approach A from the left or right, it has to approach positive or negative infinity, and that's what classifies it as a vertical asymptote. Okay? Now, this is where it's going to be fun. Are you ready? I'm ready to take that definition to the 2nd grade class and show them why that other definition doesn't work. So here you go. You guys are the 2nd graders today. Except for you're way smarter. All right. Limit as x approaches a of f of x exists. What did we say this means? Both sides approach the same thing. What does that blow up down here? What does that get rid of? No, be careful, think. But be careful.
Just at that particular spot.
If the left and right agree, which one of these discontinuities does it eliminate? A jump. Think about it. If the left and right agree, you can't have a jump. You only have a jump when the left and right what? Don't agree. Okay, if the left and right don't agree, if they don't meet up, you've got a jump. If they meet up, there's no jump. This always eliminates a jump. Every time. If the left and right agree, you're going to get rid of the jump. Okay? Now, I can't guarantee the other 2, but I can guarantee you can get rid of a jump just by the limit existing. Okay? Remember those problems where we did like A, B, C, D, F, G, A, B, C, D, E, F? Okay? And remember you had like the limit as x approaches 3 from the left was 2, and the limit as x approaches 3 from the right was 2, so then the limit as x approaches 3 was 2. But did that mean f of 3 had to be 2? A lot of times f of 3 was undefined. But this at least got rid of the what? Jump. When you showed the left and the right agreed, then the limit had to exist, and those two things had to meet up. It probably was a hole there, but they did meet. So you can get rid of the jump. All right, number 2. So limit exists, gets rid of the jump. Number 2, f of a. I want you right beside that. Defined. F of a is defined. So that goes back up to here. Suppose f is defined in the neighborhood of a. We already dealt with part A, the limit exists, so we're kind of going through this step by step. So we did that. Now where the function is defined. So it's defined. What do you think that gets rid of?
Point.
Could be point or it could be either one.
Here's the deal. It sometimes gets rid of a point, and it sometimes gets rid of an asymptote. I think it gets rid of an asymptote more often than a point. Okay? Because the only time it's not going to get rid of an asymptote, think about it. If you define the value, a for that function, if you define the function at a, if you say f of a is defined, can there possibly be a vertical asymptote? There's only one situation I can think of where that would happen, when it's piecewise. You have something like this, and you put a point on top of the asymptote. That's the only time I can think of when f of a would be defined and you would still have an asymptote. That's the only situation I can think of. So f of a almost always is going to get rid of your VA. Most of the time it will get rid of this, but it's not guaranteed. And some of you are like, well, it's going to get rid of the point for sure, because if you define it, well, I don't agree with that either. Here's why. So far, all we've done is 1 and 2, saying the limit exists and the function is defined. Let me show you one where the limit exists and the function is defined and where it's still discontinuous. You ready? Are you ready? Because right when I draw it, you're like, oh yeah, what do you think about that? There it is. X approaches A. Does the limit exist? Got rid of the jump. F of A, defined. Did it get rid of the hole? This is why the moreover comes in. Moreover, now we'll go to the third part. The value of this limit has to be what? Which is the third part of your continuity. Now, this for sure gets rid of continuities and the way they can it gets rid of every discontinuity and the 3 different ways it can manifest itself. Okay? It can be a hole, a jump, or a VA. If the first one's true and the second one's true and the third one's true, now this completely eradicates any kind of discontinuity. Because now what we're saying is, guess what? This little situation we just had, I'm now saying, hey, the limit exists. I'm saying f of a is defined, but I'm saying f of a actually is what the limit is. So you move that point right down there and you fill in that hole, and now it's removed. Now it's continuous. In that other situation, somebody were like, what about that one with the asymptote where the point was on it? Well, that one right away didn't work because the limit from the left and right didn't what? Agree. So that one really doesn't work. You'd have to make the limit from the left and right agree first, and then you could get to work on it. So you'd actually have to change the graphs here. This wouldn't even be possible to remove. Okay? And there's something called removable, non-removable discontinuity. We'll chat about that tomorrow just a little bit. It's not a big deal. But does that make sense? Do you feel like I just knocked that out of the park? Because I did. That was good. I felt really good. Anyway, let me go ahead and give you some common sense type stuff, and then let me go to the homework. First of all, when you're looking for continuity, like I said, it's easier to prove discontinuity than it is continuity. Find where it's discontinuous and then say, hey, it's continuous everywhere else. Now, a lot of times, the problem, there's going to ask 2 types of questions. Some of the questions are going to just say, describe continuity for the whole function. And when you're asked to do that, you're just going to have to locate all of the discontinuities. And once you find those, then you can say it's continuous everywhere. There are some problems where they're only going to be interested in one point. And you're just going to be asked to prove continuity for that specific point. When you're asked to do that, you're going to prove it by going through these 3 things, checking these 3 things at that point, checking to see the limit exists at that point, checking to see the function is defined at that point. And then when you do that, it's kind of like there's problems, A, B, C, D, E, and F. Remember that? Remember when A, B, and C, if it was like 2, 2, 2, That meant there was no jump. And then all of a sudden, if you said that the function was also 2, it was a perfect graph. You remember that kind of? No? It kind of always was continuous. So that's what that's really saying. If I can get the limit to equal, the function to be defined, and then if those two things are actually equal, bam, you got continuity. So if you want to show it at a point, you have to run through these 3 things. That's why I'm saying that's so important. Now, let me give some common sense stuff. First of all, when I'm looking at the whole spectrum of continuity, and the way continuity, discontinuity is manifested out in different types of functions, I think of my common graphs. And I'm going to just give you some common sense, common graph type stuff. It's so funny. Common sense type stuff to deal with when you're talking about your common graphs. First of all, polynomial functions. Love them. Absolutely love them. Because anytime I see a polynomial, I'm thinking, I don't have to fret at all. It's no, oh my gosh, oh my gosh, oh my gosh, end of the world, Dr. Pepper, where are you? Okay, it's a polynomial. What do you know about polynomials?
They're continuous everywhere.
They're continuous everywhere. They're nice, smooth, well-behaved curves. They're perfect little children. Okay, they don't ever get in trouble with mommies and daddies. Okay, they're like boring children. Okay, you don't have no fun with them. I'm just kidding. I want those kind of kids. You're well-behaved. They're predictable. You know what they're gonna do. Okay, well-behaved kids. All right, continuous everywhere. There's no breaks in that child. Okay, there's no jumps. They went from this crazy, normal child to crazy. Okay, I mean it's just perfect. All right, it's nice smooth curves. So that's polynomials. That's common sense, right? Think of rational functions, fractions. What do you think you're going to think about when you see a fraction? 0 in the denominator. Can't have 0 in the denominator. But what if you got 0 in the denominator and only the denominator? Then you know it's going to be a VA. Okay? What about 0 on top and bottom? Then you know you're going to get a whole. So you know when these two are going to kind of manifest themselves is when you get 0 just on the denominator or when you get 0 on top and bottom. And you might want to write some stuff like that down. That's up to you. I'm not going to make you do anything. It's up to you at this point. What about jumps? When are you going to see jumps? Tell me situations, common graphs, piecewise, greatest integer function, step function, which by the way, doesn't even look like a piecewise function. When you look at the equation, you're like, where's the piecewise? Well, it just shows up as piecewise. It's just the way it is. It's an aspect. Okay. What else would be an example of a piecewise function that really doesn't show up as a piecewise function, but it is absolutely a piecewise function? Absolute value function. That's all over it today. Absolute value function is another piecewise function. Does it always show up as a jump, though? No, it does. It will show up as a jump at times, but not always. Does the bird show up as a jump? No, that one doesn't, but there are the ones that have absolute values in it that I guarantee you will have a jump. In fact, there's one on your homework tonight. Okay, so absolute values can be jump. Piecewise can be jump. Greatest integers can be jumps. Can you think of any other things that jump around? Jump around. Jump. I tried to get Thomas in, but he's just not. Okay, you just look tired. I know. Sorry. Sorry, we're doing the theory stuff today. It is kind of a drag. But what else? Can you think of anything else? Okay, let's think about some other things. What about trig? What do you think about trig? When you think trig, what do you think? Which one do you think is going to show up? No. What type of stuff showed up in trig? Asymptote showed up with trig. All right, let's go to e to the x. Just trying to go through all your common graphs here. E to the x. What did you get in e to the x? That's just a horizontal asymptote. I don't have horizontal asymptote on here. I wonder why I don't have horizontal asymptote on here. Because you can cross a horizontal asymptote. Because a horizontal asymptote is not represented in the defined value. Horizontal asymptote is just what's happening at the ends. Okay? I care. Okay,
You will.
I will in a second. What else? Anything else? What about log?
That's a vertical.
That's a vertical asymptote. So you can kind of start to think about square roots. Square roots could cause problems eventually if you get negatives underneath square roots, but they're continuous everywhere from the positive reals. And usually with square roots, there's a little bit of a trick we do on them. We just say it's continuous for half of infinity, but still is what? Infinity. You just say it's continuous from 0 to infinity. So you don't really worry about the negatives. You say, okay, it's not continuous for the negatives because we know we get negatives underneath square roots, but it's continuous wherever it's positive under the square root. Okay, so you kind of start to grapple this a
Maybe it
little
seems
bit.
super long.
Okay, log, same thing, exact same thing, but you also can't have 0. All right, before this battery dies on me, okay, how much I got left? Say, come on. Does that say 5 minutes?
5 seconds.
No.